Hello, today I'm going to explain how electrons occupy orbitals. And to do this, I'm going to explain the Pauli exclusion principle, the Hund's rule, and the Aufbau principle. So first, let's start with the Pauli exclusion principle. What does this principle say? It says that the definition of this principle, no two electrons in an atom may have the same set of four quantum numbers. What does that mean? So here I'm giving the orbital diagram notation of potassium, 19 electrons, and this is their distribution in the orbitals. What does it mean that no two electrons in an atom may have the same set of four quantum numbers? The four quantum numbers are N, L, ML, and MS. So N is the principal quantum number, so this is the energy level. So the energy level occupied by the electron. So for example, let's look at those two electrons over here. Okay, so for the first one, I'm going to highlight on the first one in which I will represent the four quantum numbers. So the N of this highlighted electron is equal to 2 because this electron is in the P and specifically the P of level 2. And next, L is that where is exactly this electron? This electron is in P, not in S or in D or in F, it's in P. So the L of this electron is equal to 1 because for S, L is 0, for P, L is 1, for D, L is 2, and for F, L is 3. So here, the orientation of this electron is in the P sublevel. Now, this sublevel is divided into 3 orbitals. 1, 2, 3. 3 boxes. Okay, where exactly this highlighted electron? It's in the first ML, or you may call it PX, or -1, because this one is -1, this is 0, and this is +1. For S, the ML is simply 0. For P, the ML is, we have 3 orbitals, so it's going to be -1, 0, and +1. For the D, it starts from the -2, -1, 0, +1, +2. So this electron has an ML of -1, and the MS, which is the spin of that electron, it is directed upward, meaning +½ Now let's try now to write the 4 quantum numbers of the electron that is next to it. So again, the N is 2 because this electron is in energy level 2, principal quantum number 2, and it's the same L equal 1, and it's the same orbital -1. However, this electron has a downward spin, and the MS is equal to -½ because due to the repulsion between electrons cannot have the same spin in the orbital. Okay, so the orientation of the electron spin is quantized, and it can only be in one direction or its opposite. So either clockwise or counterclockwise. So what does it mean? Again, let's read this definition. No two electrons in an atom may have the same set of quantum numbers. So if you look at those two highlighted electrons, they have the same N, the same L, the same ML, but they cannot have the same spin. In other words, you may understand Pauli exclusion principle you may read it in another definition telling you that in an orbital, I cannot have 2 electrons with the same spin, like this, or both of them directed downward. Because if the electrons had the same spin at this point, they will both have MS of +½ or both MS of -½ So in filling the orbitals, you cannot put the half arrows in the same direction. They must be in opposite directions. And this is explained by the Pauli exclusion principle. Now, moving on, before I start with Hund's rule, I would like to explain to you the term degenerate, or you might know it as the sublevel splitting. Okay, so degenerate orbitals are group of orbitals with the same energy, meaning the same principal quantum number and angular momentum quantum number L. So they might have the same N and L, but different ML. What does that mean? Okay. Now, I can talk like when electrons, I don't want to go in details in this. I will be posting a video to explain the reason behind the degenerate orbitals. But for now, I'm just going to explain what does it mean degenerate orbitals. Okay? So first, when we look at the orbitals in every energy level, when they are not filled with electrons, they all have the same energy. They are all on the same level. Okay? However, when we start filling those orbitals with electrons, three things happen. Coulomb's law, we have to take it into consideration. Shielding effect, which describes how one electron can shield another electron from the full charge of the nucleus, and the penetration that describes how one atomic orbital can overlap spatially with another, and thus penetrating into a region that is close to the nucleus. Okay, I'm not going to discuss this right now, but I will be posting a video separate to explain those three concepts. But let's look at the 2s and the 2p. The energy of the electrons filling the 2s and the 2p are not degenerate. However, in the 2p, I see three orbitals. The electrons here and here and here are all having the same energy. Thus, we describe them as degenerate. Okay? So, degenerate electrons are electrons having the same N and the same L, but different ML. So, the electron here is degenerate with the electrons here and degenerate with the electrons here, because the electrons here, they have the ML of -1, and here they have the ML of 0, and here the ML of +1. Okay? Again, also the electrons in the D, the electrons filling the D are called degenerate. So, this is ML -2, this is ML -1, 0, +1, and +2. So the electrons occupying the 3D are described as degenerate orbitals. But you cannot tell me that electrons of 3s and 3p are degenerate. No, they are on different levels. Okay? So, let's move on. So, as I mentioned, in order to understand why the sublevels split in this way, we must examine three key concepts associated with the energy of an electron in the vicinity of a nucleus. And these concepts are Coulomb's law, shielding, and penetration. I will be doing this in a separate video. Now let's move on to Hund's rule. First, what does it say? What does it say? It states that when filling degenerate orbitals, now that you understand what does it mean degenerate orbitals, yani when filling the 3p, the 4p, the 5p, the 4d, the 3d, when filling the 2p, electrons fill them singly first with parallel spin. Okay. How is that? Let's fill the electrons of the 1s and of the 2s. Of course, according to Pauli Exclusion principle, you have to put the half arrows in opposite directions. Now, when filling the 2p, according to Hund's rule, you have to fill the electrons singly. One electron in every orbital. Then if you still have more electrons, you start pairing them. Again, let's fill the 3s. Let me focus on the 3p. It's wrong to fill the electrons like that. If I have 4 electrons, I wouldn't put them in the p in this way. Instead, that's what I'll do. 1, 1, 1, those are 3 electrons. I fill the orbitals, I fill the degenerate orbitals with single electrons of parallel spin, but because I still have electrons, then I start pairing. Now let's look at the D. Let's say I have here 7 electrons to fill. Will I be filling them like that? 4, 6, 7? Definitely not. When you fill the electrons in the 3D, when you are doing those degenerate electrons, you fill them singly first. So 1, 2, 3, 4, 5, 6, and 7. And that is the way of Hund's rule, and so on. Now, let's move to the last principle, and that is Aufbau principle. The Aufbau principle states that electrons fill lower energy atomic orbitals before filling higher energy ones. And this principle is very simple, meaning I cannot start filling the 2s with electrons and the 1s is still empty. So if you have, let's say, 13 electrons, this is how you fill them. You go in order from the lower energy to the higher energy. So 1, 2, 3, 4. Now look here, I'm going to apply Hund's rule. 5, 6, 7, 8, 9, 10, 11, 12. And now is the 13. I cannot skip the 3s, for example, and put those electrons like that here. No, I have to go in order. And for this reason, this is the order we follow when filling the electrons in the orbitals. Or simply, you can read it from the periodic table. Now, before we end this video, I'm just going to give you some questions. Which rule is violated over here? Now, let's look at this diagram. There's nothing wrong with the 1s. There's nothing wrong with the 2s. But what's wrong with this one? And which rule is it violating? This one is violating Hund's rule. Because when you are filling the orbitals with electrons, here I have 4 electrons. When filling the orbitals with electrons, you fill them singly. 1, 2, 3, then you start pairing 4. So this is how it should be. This is how it should be. So this one is violating Hund's rule because they started pairing the electrons. The second given example. There's nothing wrong with this or this or this. Also, the order is correct. But if we look at the 3s, we are violating Pauli Exclusion principle. And how is that? We said that there are no 2 electrons having the same 4 quantum numbers. And those 2 electrons over here, they have the same quantum numbers. So for both of them, n is a 3. For both of them, L is 0 because it's S. For both of them, ML is 0 because there's just one orbital. And for both of them, the spin is up. It shouldn't be. It's plus half. One up and one down. It should be in opposite directions. That's how it should be. So this diagram is violating Pauli exclusion principle. Again, the third diagram over here is violating Hund's rule. They paired the electron and this one's still empty. You cannot fill the orbitals. You cannot start pairing the electrons in the orbitals unless you're done with your first round. You fill electrons singly, and then you start pairing them up. Of course, with opposite directions of the half arrow. So this one is violating Hund's rule. Finally, last question. According to the Aufbau principle, which of the following sublevels is the lowest in energy? Now you might think of this 4D, 4S, 4P. They are on the 4th energy level. Yes, true. But they're not like when we go, there's like splitting of the orbitals, so they do not exactly have the same energy level. Now, when I look at the periodic table, S is always the one with the lowest. So here I have 4S. And here I have a 3D. Am I going to choose the 3D or the 4S? What happens? S penetrates more toward the electron. And according to Aufbau principle, in the diagrams, in the orbitals, 4S comes first, followed by 3D, followed by 4P, followed by 5S, and then 4D, and 5P. So that's the order. So here it comes 4S before the 3D. Again, the 5S before the 4D. The 6S before the 4F and the 5D. So that's how it is according to Aufbau principle. So in this question, my answer, which comes first, it's 4S. For more questions, please write them in the comments. Thank you for listening.